Thank you for that introduction. Also, I want to acknowledge that the land I am on is traditionally the land of the Monacan people who still are alive and thriving today. This is a nation that has just been federally recognized as of 2018, although the first maps produced by Captain Smith included the Monacan Nation on those maps in the early 1600s. And so one of the issues that the Monacan people are working on now is to save the former Monacan capital, which was also a trading center. So if you're interested in those issues, feel free to check out U.S.A, and there are petitions you can sign, and just really useful to have more names on those petitions. And I also want to thank all of you who are here, especially those who have already had a full workday or are cutting into your sleeping hours to be here. And as someone who has never taken a glaciology class, everything I have learned is self-taught along the way. And it's really an honor to be here. This also gets me out of a very long faculty meeting. And so today, what I chose to bring to you all is landform evidence of meltwater discharge at paleo grounding lines, and really sort of extracting what I can reconstruct and my colleagues can reconstruct from these landforms about processes that are useful for thinking about contemporary glacial systems. And so let me just use my four Zoom hotkey to remove the floating bar real quick. Here we go. Right, one challenge, a global challenge, is to be able to predict sea level moving into the future. And a huge piece of that puzzle is understanding how ice sheets will respond to climate forcing. There's a lot of variability in terms of grounding line positions, both spatially and temporally. That's important to think about. I really like this plot right here from Conrad 2018 that shows spatial variability across individual grounding lines for regions, for glacial systems around Antarctica. Right, and so there's a lot of variability in position of grounding lines and the rates of migration, and really observations show that there's this variability in grounding line positions really at the finest scales observable. And so one question that I think about is, what sort of spatial and temporal scales do we really need to know about for better predicting grounding line behavior moving into the future? And so we know that there are a lot of processes that take place at grounding lines, and a lot of conditions that also impact grounding lines. And so this schematic that I've put together summarizes some of those, or introduces some of those. Oops, there we go. We really need to understand not only these individual processes, but how they interact with each other. And of course, these processes and conditions are changing on a variety of time and space scales. And so sort of mashing all of these together and trying to think about, well, what is the outcome in terms of how grounding lines are going to respond to these processes and conditions. And another question that I spend time thinking about and try to address in some ways in the research that I do is really thinking about if there are certain processes or conditions that lead to a sort of predictable grounding line response based on the geologic record of past grounding lines, right? So are there certain bed settings or ice shelf configurations or ocean conditions that lead to some sort of predictable or consistent grounding line behavior? And so what we're going to do today is first talk about why someone like myself would spend time studying these geologic archives of glacial ice when there are certainly contemporary systems today that can and are obviously studied. And then the next part will be to think about how ice marginal landforms are built, right? These are the landform signatures of paleo grounding line positions. And so that's important context for thinking about understanding how water is draining from the subglacial environment across the grounding line into the ocean. And then we will talk about a channel system on the Antarctic continental shelf that is fed by subglacial lakes, and the grounding line response to that water draining at the grounding line is in the form of production of embayments, and so we'll talk about why that's significant. And then we will move into a case study of persistent drainage at a retreating grounding line marked by hundreds of ice marginal positions, and the influence of bed topography and slope on that drainage. Okay, so, and you can keep track of where we are in these 4 parts by these numbers down here. So if you're thinking to yourself, oh gosh, when will she ever end? Well, you will know by these numbers. So why study geologic archives of glacial ice, right? So these archives are very useful for gathering long-term context for contemporary glacial systems, right? So we can observe the state that glacial systems are in today, but what led to that current configuration or current state. We can also think about a range of possible outcomes. So these landform signatures are really recording the outcomes, sort of the final event. And it's really useful for thinking about grounding line behavior and patterns of retreat, and these patterns and behaviors that we can use to think about contemporary systems. And also, deglaciated environments are generally easier to access, right? That's not an unconditional statement, but generally they are easier to access, right? So if we want to think about subglacial environments or these grounding line environments in deglaciated regions, right? There's not hundreds of meters of ice to worry about getting through to access these environments. And I should say that most of what I do is thinking about the most recent deglaciation, right? So this nice map that I use in almost every talk and in lectures as well shows the configuration of last glacial maximum ice sheets. And so all of these regions on the continental shelf that used to be covered by ice, these are all regions that I think about. Okay, so landforms are really, you can think of the footprint of glacial systems, or in this case, I'm talking about ice sheets. And they record not only how that ice retreated across the landscape or seascape, but they also record processes. And today we're talking about landforms. I also think about sediments, and especially if we couple those two, the sediment records and the landform records, we can really extract a lot of information about ice behavior and processes. And so if you have read this recent paper of ours, you'll recognize this figure. This is a sort of summary figure for stating how we characterized glacial landform assemblages across deglaciated continental margins worldwide, but also just highlights the range of behaviors that we can extract from these landform records. And today, we'll be focusing on these ice marginal landforms, and here are some examples of those. Right, so ice marginal landforms mark former grounding line positions, and allow us to identify these outcomes that I mentioned across timescales of years to thousands of years. Okay, so now thinking about, well, how do we have to think about these ice marginal landforms? And it's important to state that these are basal expressions of former grounding line positions. And so we can look across individual ice marginal landforms or in the lateral space and think about spatial variability, but we can also track temporal variability in grounding line behavior or processes if we can track that retreat across the landscape. Right, and so this is different than most of our observations of contemporary grounding lines, which are viewed from the surface. And so one question that I think about but really have not addressed is, are the basal expressions of grounding lines the same as the surface expressions? And what I mean by that is the morphology or the shape of the grounding lines of the surface similar to the basal expressions. And so one project that I am currently working on with Lee Stearns and Kaya Riverman is thinking about what conditions lead to lateral sinuosity in grounding lines, both thinking about the paleo, the landform record, and contemporary grounding line systems. So maybe eventually we'll get to a point where we can say something about these basal expressions and whether they're similar to the surface expressions or not. So how do ice marginal landforms form? The two types of ice marginal landforms that you will be hearing about today are recessional moraines and grounding zone wedges. And so for recessional moraines, right, these can form both in terrestrial environments, but also marine environments, and are thought to generally be a result of deformation, like push at the grounding line, but also from deposition of sediments coming from the subglacial environment and being deposited at the grounding line. Whereas grounding zone wedges, on the other hand, are thought to be generally constructional, right? So sediments are moving in the subglacial environment, being deposited at the grounding line. And for grounding zone wedges, they both, the sediments build up or aggrade and they prograde out. So one important distinction between recessional moraines and grounding zone wedges is that these grounding zone wedges are thought to lead to stabilizing feedbacks for the grounding line. So as sediment is building up and moving out, it's thought that the ice can advance seaward, where if you don't have these sediments building up, it might not do so. Okay, and so one question is, are these two types of landforms, recessional moraines and grounding zone wedges, are they really genetically distinct landforms? And what can they tell us about processes causing retreat and styles of retreat? And so my collaborators and I chose to address these questions using over 6,000 ice marginal landforms in the Western Ross Sea, Antarctica. And if you're not familiar with working offshore of Antarctica, the Ross Sea is really the place where we have the most coverage of bathymetry data on the seafloor. And so in no other place around Antarctica can you look at this many ice marginal landforms. Okay, and so when I gave a talk recently, I got a question at the end about, well, where does this sediment come from? And so I thought I would address that now. So sources of sediment being deposited at grounding lines, that can come from the deformation till layer and be deposited at the grounding line. It could also come from sediment gravity flows that could mobilize some of that material. For example, at the foreset of these grounding zone wedges. But also we know that sediment accumulates in these ice marginal grounding line environments as sediment is melting out of the basal ice. Just for those of you who are not familiar with sediment cores or don't look at sediment cores, really useful techniques for thinking about these grounding line sediments are both X-ray images of sediment cores and more recently looking at CT scans of sediment cores. This is showing examples till that's being deposited at the grounding line. Okay, and so looking at these 6,000 different landforms, over 6,000 landforms in the Western Ross Sea, we see that really both of these types of landforms show evidence of both deformation and deposition being important in their construction. And so this shows little patches of multi-beam bathymetry data here, and here that has centimeter to decimeter scale vertical resolution. And all of these are gridded at 20-meter horizontal resolutions. And then with these cross sections that you see here, which are indicated in each of these little postage stamps. This is sub-bottom profiler data, where we can see this is a nice case of recessional moraines, and they are being deposited on top of a reflector. This reflector is generally thought to be associated with ice advance across the continental shelf, and then sediments being deposited on top of that either during glaciation or during retreat. And we can see the same for some observations of grounding zone wedges deposited on top of that surface here, but we can also see evidence of deformation of those sediments that are forming very similar types of landforms as their seemingly sort of purely depositional counterparts. And one observation that we came across that was quite surprising was that there are very abrupt transitions between these end member landforms, being the grounding zone wedges and the recessional moraines. And this is a case where retreat is proceeding in this direction. So each of these lines that you see here, or these breaks that you see here, these are representing retreat going in that direction. But we can see that the character of those landforms change between what you would visually characterize as a grounding zone wedge and what you would visually characterize as a recessional moraine. And so as the grounding line, this is a retreat sequence, so as the grounding line is retreating in this direction, we see that there are lateral shifts between these landform products. And what's interesting here is that this is suggesting spatial transitions across single time synchronous grounding line positions. And the landform morphology that we see here and the rates of retreat can vary across this paleo grounding line at sub-kilometer scales. And so just to make that point, right, so within this space, we see that the grounding zone wedges, individual grounding zone wedges contain about 8 times more sediment than the moraines over here. And on the moraine side, we see that there are 2 times more landforms. So across a single grounding line, it's retreating asynchronously across this space, where the grounding zone wedges contain more sediment and reflect more time that the grounding line was parked at those locations. Over here, we see that the grounding line was retreating more rapidly. We also see that there are temporal transitions within a grounding line retreat sequence that indicate that there are really quick changes in the processes that lead to landform growth and overall morphology. In this case, we have grounding zone wedges over here, and then there's some across a space of a couple kilometers, and there is a switch to those recessional moraines. And honestly, if anyone has an idea of what these features are, my colleagues and I have spent hours talking about these. So if that looks familiar to anything that you have seen, please let me know. Okay, so what does their morphology tell us about grounding line position stability? And when I say stability, I'm really just talking about, is the margin the grounding line stationary, or is it retreating? And so we see that these landform products are sensitive to sediment flux and to grounding line occupation times. We also tested thought about whether the presence of an ice shelf was important. It has previously been suggested that these recessional moraines, that the grounding zone wedges form in an ice shelf environment, and therefore have this sort of smeared out appearance. But the recessional moraines that we see, or the grounding zone wedges that we see in the Western Ross Sea, are much larger than the recessional moraines, so that hypothesis doesn't hold here. And so really it's sediment flux and grounding line occupation times. What we see are two distinct styles of grounding line behavior, even though that these landform products are genetically sort of related, or end members you can think of. We do see that there are two distinct styles of grounding line behavior that varies abruptly across time and space. So the first is small magnitude retreat events that appear to be driven by cyclic or regular processes that are forcing retreat. And then for the grounding zone wedges, these longer durations of grounding line position stability that seem to be enhanced by landform growth, but result in larger magnitude retreat events. And so now what we're actually going to be thinking about is thinking about the channels that you see here. There's also another channel here, moving on to another part of the talk. Right, we have to know what these paleo grounding lines look like before we can think about channelized meltwater drainage at grounding lines. And we know from contemporary observations that channelized meltwater drainage at grounding lines can alter ice shelf mass balance. And we also know that they can deliver sediments to the grounding line and beyond, which these typically very fine grained sediments contained within meltwater plumes contain a lot of iron that's important for the critters that are living in the ocean. And so what does the landform record suggest about channelized meltwater drainage at grounding lines? And what if we can map entire or seemingly entire drainage systems and see how they influence grounding line behavior across long time scales? And so the results that I'm showing you here are coming out of this paper, where we tracked a channelized drainage system to its upstream source, being a series of subglacial lakes on the deglaciated continental shelf in the Western Ross Sea. And so just to provide an overview, sorry about these colors, what we see here is in the yellow, we see mapped channels. In the orange and pink or purple, we see mapped ice marginal landforms. And then in the green, we see subglacial lakes. And so what we're going to do is we're going to start over here and then work our way to the source subglacial lakes. Okay, so one important thing in doing this type of work is to be able to establish the timing of of active drainage within these channels, which can confirm whether they are paleo subglacial channels or not. And so what we see is that this channel right here, I'm not showing the acoustic, sub-bottom acoustic data, but this channel here is incised into that, that reflector I mentioned associated with ice advance across the continental shelf. And we also see that in this panel right here, that the recessional moraines are overprinting the channel. And so this constrains the timing of active drainage in this space right here to before when the grounding line retreated across this part of the seafloor. And so we can actually track this channel system here all the way to a large ice marginal landform, a grounding zone wedge that is associated with a relatively significant advance of the grounding line, at least 50 kilometers. And we can tell that because we see these prior retreat assemblages here being overprinted by this large grounding zone wedge. Right, so this grounding zone wedge is in part overprinting this drainage system, but if you squint your eyes or just trust me in mapping this out here, that this sort of ancestral part of the channel system is sort of reborn when this grounding zone wedge is being deposited and constructed. And so you can see, or maybe not see, but trust me, you can see a channel that's incised into the top of this grounding zone wedge, and it leads directly into a pretty large embayment. If I remember the numbers right, it's like 9 kilometer at most embayment. And so these embayments are really marking sites where local ice advance due to the growth of the grounding zone wedge, where that is being reduced, right? So over here, the grounding line is capable of advancing in the seaward direction and here as well. But those sediments are not being deposited within this embayment. We do have sediment cores, and so we can confirm that it's not just erosion of the grounding zone wedge, that it is a true area of non-deposition. That this part of the grounding line is inhibited by that sort of self-stabilizing process. There's also another embayment over here, and we can keep seeing those, and in this case as ice is retreating in this direction. And so this is a schematic adapted from one of Richard Alley and colleagues' papers in 2017 that suggests, in fact, that the growth of these grounding zone wedges can allow the ice to advance. And so going back to thinking about how we think about grounding lines, I think we tend to think in this sort of cross-sectional space, or at least I formerly did. And we really need to understand what's happening sort of in and out of the computer screen or phone screen, whatever you're using to catch this talk. So looking at this lateral variability is also really important. But in this case, right, so the channelized drainage is restricting that self-stabilizing feedback. And so the relationship with these ice marginal landforms across this channel system allow us to estimate the frequency of drainage events. And in this case, we see that the frequency of drainage exceeds the duration of recessional moraine construction. We always, in this case, we always see those small recessional moraines overprinting the channel system. And at most corresponds to the timing of grounding zone wedge formation, which is quite variable. And so to figure out the sort of maximum duration between these drainage events, what we use is that the largest ice marginal landform that is bisected by the channel. So in this case, the one with that large 9-kilometer or so embayment. So we take the sediment volume within that landform based on our sub-bottom acoustic data. And then we use a range of estimates for grounding line sediment flux coming from a number of different sources. And we can say that the maximum landform construction time is depending on what sediment flux, 80 and 500 years. And so that allows us to say that drainage events occurred on these sort of decadal to several century timescales. Most of the ice marginal landforms are in fact much smaller than this one that we use to estimate sediment volume and construction times. And so just to be conservative, order of magnitude, right? Decades to several centuries, this episodic drainage moving through this channel. And so now moving up to the source subglacial lakes, this channel does track all the way back to these subglacial lakes. And so we use that acoustic data to identify these as lakes, so typical sort of parallel laminated sediments. We also see a fan, meltwater fan type deposits here, and we do have sediment cores as well to confirm this, and especially on the top of this feature, we have identified a grounding zone wedge, and so we know that ice was covering this region, and that the channel tracks back up here. And so doing a bit of analysis in GIS programs, right, we identify a series of subglacial lakes. Most of these are actually very small, so they have depths of 4 to 20 meters, and if we sum up the volume capacity of all of these lakes, it's about 2 cubic kilometers. And then just in cross-section space, you can see those little basins. And so based on the channel morphology, we estimated bank full channel discharge. And based on that discharge, we estimate that these drainage events that are making their way all the way to the retreating grounding line would have lasted about half a year. We also do a little bit of modeling and estimate that geothermal heat fluxes and basal melt rates above these subglacial lakes are reasonable to fill these lakes at decadal to centennial timescales. Okay, so finishing up with part 3. So we see that channelized drainage locally restricted landform construction and contributed to this spatial variability and grounding line stability. We also see, these observations support the possibility of these embayments forming, which creates pronounced grounding line sinuosity, which inherently just opens up the grounding line to be in more contact with the ocean. And potentially likely feedbacks with plume-driven melting may have collectively led to retreat. We also see, if you remember back to that sort of overview, bathymetry map with all of the mapped landforms, the retreat pattern follows this drainage system all the way back up to the subglacial lakes. And so whatever mechanism is causing the grounding line to retreat up to the source subglacial lakes, we don't know, but there does appear to be an influence of this drainage system and the subglacial lakes on controlling the pattern of retreat. Okay, so thinking about styles of drainage, we can broadly classify different styles of drainage as fast or efficient channelized systems and slow, inefficient distributed systems. And this is very important information, right? So what is the type of drainage system? Is it allowing water to be transmitted quickly or not? Which is important for understanding the ice response to that meltwater transmission. in the subglacial environment. We also know that there are temporal shifts in the style of drainage, in this case, over the melt season in Greenland. And there are also spatial shifts in the drainage system. And so we really need to have perspectives across time and space that capture this evolution of drainage systems, both together and separately, to understand what is the sort of real range of plumbing we can expect beneath different sectors of glacial systems. And so in the paleo record, there are a few examples. Actually, let me be fair. So I'm showing you 3, but there are 4 examples of what are called meltwater corridors. And really what these are, they're an amalgamation of different drainage styles along broad and persistent pathways in the paleo subglacial environment. And so all of these observations, these 4 observations, 3 that I'm showing you, are from the Northern Hemisphere, but none of them are explicitly linked to meltwater drainage at the terminus of paleoglacial systems. Some of these examples are on land and some are in the ocean. And so also in the Ross Sea, we see an example of one of these corridors. It is very important to state, right, we are seeing the footprint of these drainage systems. The ice no longer exists, so we don't know how much incision of these channelized drainage systems occurred into the ice. But looking at this footprint, we see a collection of 72 sediment-based channels present on the Stoss or upstream side of a topographic high. And so this is we're moving up onto the topographic high, and then what you don't see off the page is that this survey right here is really sandwiched between 2 different banks that likely contributed a lot of lateral influence on the ice that was flowing across this landscape. And so here we see these are the mapped channels, just showing the mapped length of individual channel segments, as well as all of the ice marginal landforms that are either overprinting down here or are incised by these channels. So these cross-cutting relationships with ice marginal landforms, again, allow us to determine when the channels in this corridor were active. And we also have sediment cores across this space too that help us identify the timing. And we do see a large sediment accumulation at the terminus of this corridor that suggests that meltwater drainage was flowing. This was upstream part, so meltwater was flowing in this direction. So we call this upstream and we call this downstream. So there are interesting changes in corridor morphology that correspond to bed topography, right? As ice was flowing up and over this bed topography, it likely, being a big topographic high, likely had an influence on ice thickness, ice surface slope as well, right? But we're looking at the footprint of these channels and the bed topography. And so what we see is that downstream, so moving uphill, that there is an increase in the number of channels and the distribution or the space these channels are taking up, as well as incision depth. And so these are profiles taken from the upstream-most part of the corridor to the downstream-most part of the corridor. And each of the base or the thoweggs of those channels has a dot right here. So where you see these dots, you can think about incision depth and presence of these channels. And so we see that these changes in channel morphology that we see in the number of channels really corresponds to a jump in positive relief of tens of meters. So here now we're looking at sort of a long meltwater or ice flow direction. So here's the upstream part of our channel system. Here's the corridor, and here is the downstream most part of that corridor. And so water and ice were both flowing in this direction. And we see, so you can look at these numbers and colors over here, where we have the biggest change in the morphology of channels at about 25 to 30 kilometers downstream of the corridor, from the upmost part of the corridor, upstreammost part of the corridor. We see that, right, 25, 30 kilometers, we see that we move into this space where you have that big jump in positive relief. And what you see in the gray here, this is looking at bed slope. And we can also see that bed slope becomes much more variable across this space too. And so another point is that despite evidence that supports more focused flow through channel deepening, we also see that there's more distributed flow upstream. And by that, I mean that there are more channels and they're taking up more space. So right, if we look at the upstream most part, we have one channel located here. And then if we look at the downstream most point, we're looking at channels that take up five-ish kilometers of space in the across corridor direction. And interestingly, we also, again, here we use the channel morphology to say something about how much water was flowing, could have been flowing through these channels. Right, just assuming the incised part of the channels, the downward into the sediments. And so using a cumulative bank flow channel area across each of these transects that I showed on the last slide, we can think of just sort of order of magnitude bank flow channel area, which we use as a sort of indication of drainage capacity within these channels. And what we see is that drainage capacity varies 3 orders of magnitude across this corridor. It might be intuitive, right, to think that as you move from downstream to upstream, maybe you have a consistent, if there's a single source of water at the upstream or headwaters of this corridor, you could expect more or less consistent drainage capacity. Maybe you would expect increasing capacity as you move from upstream to downstream, because more water could be accumulating in this space as the channel is transmitting water, but that's not what we see. So we see that drainage capacity increases significantly and then all of a sudden drops off. These variations in drainage capacity also correspond to changes in variability in bed slope and also bed topography. Once we get to about 50 kilometers downstream within the corridor, that's when we start to see that the bed slope is becoming more gentle and the topography is flattening out. And so one question is, where does this water go? There could be a transition or more channel incision and drainage upward through the ice. So channels carved into the basal ice, potentially through shallow groundwater system. And so this gaining and losing meltwater corridor that we observe also has interactions with, it's important to think about cross-cutting relationships with ice marginal landforms. And we see that the grounding zone wedges were deposited when the corridor was actively draining water, and that there's a switch to recessional moraines about this space. So from here, all of this is dominated by recessional moraines. That is also where we see that the ice has retreated off of that that big jump in topography and down onto a gentler sloping bed. We see that this corridor is demonstrating both sort of a time and spatially evolved drainage system. We see that there are linkages between meltwater channelized drainage and bed topography. Again, this could also, in this case, this could also be a result of changes in ice surface slope as ice was moving over this topographic high and being squeezed laterally by the banks. And we see that there are these prolonged feedbacks between our active meltwater drainage and grounding line retreat. It's interesting to think because in the example, part 3 of this talk, right, that channelized drainage system corresponded to embayments within grounding zone wedges. And here, in this case, at the terminus or apparent terminus, there is increased sedimentation. And we also see that, that as the ice is retreating, there's sediment being deposited on the banks of this channel system, but not within the channel itself, until we get down to this space where the moraines are overprinting the channel system. And so we see this sort of similar relationship between grounding zone wedges being incised by these channels and moraines overprinting the channel, meaning that the channel had shut off. But in this case, we see that there's some evidence that this channelized drainage, at least when the grounding line was situated here at the top of the topographic high, that it led to enhanced sedimentation at the grounding line. Right, a big difference between what I showed in part 3 and part 4 is that part 3, that channel system was fed by subglacial lakes, and so episodic drainage at the grounding line, whereas here, if we do believe that strain heating was important in producing water, there could have been more or less persistent water drainage through this channel system, as long as ice was grounded on that grounded and flowing across this topographic high. And I did not put any transition here, so that's not so good. But because you all are here with me, I wanted to use this as a platform for something that Chris Carr, Laura Stevens, and myself are working towards. And there are many people throughout their lifetimes who change their names. And one big consideration for researchers when changing their name is, am I going to lose, all of my citations that I published with my other name, or is my sort of, will people even recognize like those publications as being mine? And so there are a number of reasons people change their names. Here are some of the maybe more intuitive ones, right? To better fit one's gender identity, marriage, civil partnership, divorce, estrangement, or adoption. But there are some less intuitive, potentially less intuitive reasons that someone would change their name. And all of these, right, could be sensitive reasons for changing a name. So adaptation of a name to another language or script, to avoid stalker or harassment, for religious reasons, to disassociate themselves from family or from others, like celebrities, and to change their name to something that they actually use. So changing their name from their given name to like a nickname that they use every day. And so I'm pleased to say that that IGS is allowing us to solicit feedback and draft a name change policy that allows for invisible name changes to protect the reasons why people change their name, and give several options about how they want to do that. And the editorial board will take this and potentially modify it and bring it forward to the Cambridge University Press. Because we publish in a lot of different places, right? It's important to think about, well, where else could a name change policy be implemented or improved to protect researchers. So I don't, Davy, can people post into the chat here or not?
Yes, they can, definitely.
So what I would love for you to do is to type the last journal that you submitted to, or if you haven't submitted an article before, I know there are students here, what is the last journal what is the journal of the last article that you read, right? And I can gather that information, and then I can check out, well, where are glaciologists publishing these days, and see what their name change policies are, and potentially solicit those journals to adopt a similar name change policy. So if you could, into the chat, type a journal that you publish in or that you read frequently, that would be great. Also, you can take it upon yourself to email editors of other journals. There's a letter template located here, iceocean.org, community building, if you want to send out letters yourself. So thank you for your time. You can find me in these various places. I also want to put a plug in for next week's talk. Jan Lennertz will be now talking about the ice surface. So scratching the ice surface, thinking about observations and numerical models. So tune back in next week for his talk.
Fantastic, thank you so much. I think there's some questions in the chat. They're sort of distributed amongst a lot of journal names, of course.
Okay.
I think there's one there from Trevor, if we would like to start the questions.
Can we identify inland sediments from subglacial lakes from Paleo Ice Sheets, or are they now under present lakes? That is, if I understand your question, that is a good question, right? So can we identify sort of source of sediments in these subglacial lakes, and thinking about how water drains from these subglacial lakes? Do they drain fully? Do they entrain the sediments that have collected at the base? Those are all very good questions. And actually sort of stemming off of a proposal that I plan to write to NSF to go to these subglacial lakes to think about how water drained from one lake to another, and to see if the sediments are being sourced from upstream lakes, or if they appear to be unique.
There's a question in the chat from Julia Wellner. Do you want to unmute yourself, Julia, and ask the question?
Okay, sure. Thank you, Lauren, for the very nice talk and a review of lots of your recent work. You mentioned that some of the grounding line landforms that you showed us could act to stabilize ice as the construction of those features grows. And then you also took us on the channels. You took us through some calculations on how long things might have taken and what's the duration of formation. I was wondering if you could try that same thought experiment for the moraines or wedges. How long do they take? And does that add any light to them potentially acting as stabilizers? Thank you.
Yeah, great question. So in the case of the Western Ross Sea, all of the grounding zone wedges are larger than the moraines. And actually the moraines are very similar in morphology and spacing to Dekear moraines. And so potentially talking about sort of annual to multi-annual retreat for those smaller features. For the grounding zone wedges, the duration of grounding line occupation for some grounding zone wedges has actually been dating. I know you know that, Julia. And so typically for last glacial maximum grounding zone wedges, we're talking about occupation times of several hundred to a couple thousand years. But in this case, these grounding zone wedges are representing less time. That suggests that through a deglaciation, right, you're sort of priming the system for retreat. Certainly during a deglaciation, temperatures are warming both in the ocean and in the atmosphere. But in terms of the stabilizing feedbacks, in the case of the Western Ross Sea, we know that the grounding line occupied those grounding zone wedges for longer. So potentially the states representing the self-stabilizing feedback.
Thank you. I think there's also a question from Olga. Olga, do you have
Thank you. Great talk, Lauren. A very naive and somewhat ignorant question. So these sediment wedges, is there just one mechanism to explain them? Or as I'm asking, are there any potential other explanations how they form? Or is it like specific evidence that they are formed when the grounding line advances or retreats?
Great question. Yeah, so all evidence points to grounding zone wedges forming at the grounding line. There's a number of evidence to suggest that. Not a lot, many times these grounded zone wedges have glacial lineations leading right up to the crest of the features. Suggesting that ice was grounded and that the break, that asymmetric morphology in the break in the slope, the crest of those features represents the true grounding line. There are other sedimentation processes that could influence the growth of these features. In some grounding zone wedges, you see more evidence for sediment gravity flows. Sometimes you see little fans incorporated onto the sides of these grounding zone wedges, but they really truly are signatures of paleo grounding lines. Some would actually refer to the whole, the across flow length of these along flow length of grounding zone wedges as being the grounding zone, but right at that crest break, that is where the last position of the grounding line was.
Thank you, Hester. I think you have a question.
Yeah, it nicely. Hello?
Yes, we can hear you.
Okay, yeah, I just don't see myself. This nicely goes on from Olga. Nice talk, by the way, Lauren. And it's kind of, it's the past is the key to the present in terms of your research rather than the other way around. So my question is about tidal movement. And when I saw your mystery kind of stripes, when you asked like what can cause this, it made me think about the iceberg plow ridges, the keel plow ridges and plow marks that Julian Dowdeswell has published a number of papers about. And then I thought about that, I thought about tidal movement. So if you have a grounding line in one position for a very long time, would you maybe have, because of the pressurization effect, like some kind of sedimentary signature, and like, is that known, or are you kind of looking for those kind of things?
Yeah, I mean, we are looking, because we know tidal processes are important for contemporary systems. Those of us who are looking at these landform records, we are looking for that sort of information, and also looking at sediments. There are sediment signatures of tidal movement, and we don't see that. But if you're thinking about sort of comparing those corrugation ridges, they go by lots of different names that you mentioned. The recessional moraines tend to be a little bit larger. They're not confined to a sort of a width of a iceberg keel, so they are laterally more continuous, and the spacing is greater between these features. So they are distinct. Without a scale bar, they could look very, very similar. One thing that we do with sediment cores is we look at sort of residual shear strength of the sediments. We also think about water content, and there's certainly paleo grounding line positions that were paleo grounding lines that were sitting on sediments that seem to have been strengthened, potentially by dewatering, maybe due to the presence of subglacial channels being efficient drainage regions, but maybe due to tides. So we are looking for evidence out there of tidal movement and how that might influence sediment properties too.
Thank you very much. Are there any further questions for Lauren? Go for it, Roger.
Thanks very much, Lauren, and thank you, Tavy. Another naive and ignorant question, though I say it's my own ignorance as a seismologist. I was wondering how disruptive and any kind of water circulation patterns, thinking in plan view, are on all the models that you present. We see these lovely 2D sections of grounding lines and the water circulation under them and so on, lovely pictures of your wedges accumulating. Is there a situation where something under the glacier and is doing its best to produce a grounding zone wedge, but the sediment is actually being moved laterally when it gets to the grounding line and the open water? The evolution of the shape of the inlets and the bays over time must have something to do with that, I would imagine.
Yeah, so that's a great question, and you picked up on something that I've included in this draft manuscript on the last part that I mentioned to you all. The grounding zone wedges in that are bisected by the channels in the corridor, they are very different. They are very smeared out, so to speak. From sediment cores, we also know that there's not a lot of, comparatively not a lot of water in those sediments. And so there is some fundamental relationship between this corridor and the morphology of those ice marginal landforms. And that's, I mean, it's quite possible that it has to do with sort of changes in thermal regime due to this water efficiently draining through the channel. I haven't really thought about sort of lateral movement of the sediments, but certainly there seems to be an influence on the landform product in this corridor and active drainage.
That's cool. Thanks very much.
Thank you. And a question from Sasha.
Got on mute. So I was curious how much thought you put into supercooling. I saw the water basically going up a big uphill slope. I thought, well, I wonder how much that's freezing on and how that's affecting things.
Yeah, so in terms of supercooling above the channels, there's not much I can do with that because the ice isn't there anymore. And I tend to not think about I tend to not think about of what I don't know, right? So we see these outcomes, and I can only deal with that footprint. It is possible, and we've had multiple conversations about channel ice drainage, and maybe we need to talk again.
I bet for that.
Fantastic. Any further questions for Lauren? I think we may have run out on the chat there, but thank you very much. And I was going to say thank you very much as well for your initiative on name changes. I changed my name. I did it before I started writing papers, at least not officially, but in practice. So it is something that can really affect people, I think, in terms of all the metrics that are used to counter.
Yeah.
So I think it's really important. So thank you very much for that.
Yeah, and I should say that Chris Clark has been working since 2018 on this. So largely her work, and I think just putting us three together to get it done has been a good way to do it.
And I saw a comment on Facebook that Doug McHale's glad that we're doing it right, or doing it well, maybe, or hopefully doing it anyway.
Yeah.
So that's great. So hopefully see everyone next week for Jan's talk on scratching the ice sheet surface, move from the bottom to the top of the ice sheet, I guess. So thank you very much to everyone, and see you next week. Thank you again, Lauren. That was brilliant.